Okay, now let's look at the second law of thermodynamics, dealing with entropy. Okay, first of all, I'd like you to make a guess here. Fossil fuel electric generating plants produce thermal pollution. Part of the heat produced by the burning fuel is not converted to electric energy. The reason for this waste is, and you've got five answers here. The efficiency is higher if some heat is allowed to escape. Engineering technology has not yet reached the point where 100% waste heat recovery is possible. Some waste heat must be produced. This is a fundamental property of nature when converting heat to useful work. The plants rely on fossil fuels, not nuclear fuel, or E, none of the above. So lock in your answer, and let's see if we can figure it out at the end. Okay, the first law of thermodynamics states that energy is conserved. There are, however, many processes we can imagine that conserve energy, but are not observed to occur in nature. For example, when a hot object touches a cold object, why doesn't the hot object take energy from the cold object, making it hotter and the cold object colder? I mean, that's possible as long as energy is conserved, right? So the one with the low energy gives up even more of its energy to the hotter object, but the total amount of energy would be the same. That never happens. So here we have this horseshoe that's hot. We put it in the water. What do we do that for? Well, it cools down the horseshoe, right? Well, why? Why doesn't it go in reverse? Why doesn't the put the hot horseshoe inside this cold bucket of water? Why doesn't it gain even more energy from the cold water? Make the water turn to ice and make the horseshoe even hotter. Here's another example of that first law. When you drop a mug, its potential energy is converted into kinetic energy, which is then converted into internal energy as the mug shatters and comes to rest on the ground. Have you ever seen it go in reverse? In other words, the the shattered mug all of a sudden reassemble itself and go back up into the air to wherever it fell off of. Why not? I mean, the energy is still be conserved. Why doesn't it happen? Hmm. Well, that's because of the second law of thermodynamics. The second law of thermodynamics is a statement about which processes occur in nature and which do not. Heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. Now let's think about a heat engine. This is supposed to be a pictorial example of what a heat engine does. So here we have the engine itself here in green. And what it does is it operates between two reservoirs of temperature. This reservoir here is a high temperature reservoir, and here's a low temperature reservoir. And what it does is it takes energy in the form of heat from the high temperature reservoir and it converts some of that into useful work. But here's the deal, not all of it gets converted into useful work. Some of it is always exhausted out the exhaust into the low temperature reservoir. So if you're thinking about your car, you got the high temperature inside your engine, and some of that is turned into useful work to make the tires spin faster so you could drive somewhere, but some of it goes right out the exhaust or radiates from the radiator into the environment around the car. The basic idea behind any heat engine is that mechanical energy can be obtained from thermal energy only when heat is allowed to flow from high temperature to low temperature. Some of this heat is then transformed into mechanical work. Heat engines run in a repeating cycle, so therefore the change in internal energy of the gas is zero. Heat engines. Why a change in temperature is needed to drive a heat engine. In the reciprocating steam engine shown below, suppose there were no condenser or pump and that the steam was at the same temperature throughout the system. Thus, although work would be done by the gas on the piston when it expanded, an equal amount of work would have to be done by the piston to force the steam out the exhaust. Well, if that happened, there would be no net work done. For a real engine, the exhaust is cooler, so the exhaust pressure is less than the intake pressure. In that case, there would be net work done. If I wanted to figure out the efficiency of my engine, really we want to look at the heat, the heat that goes in and the heat goes out and how much useful work. So the efficiency, I'm going to call it E, of any heat engine can be defined as the ratio of the work it does, W, to the heat input at the high temperature, QH. So one way to find the efficiency would be work divided by QH. Now, of course, that's going to be a decimal. Then you can multiply by 100 to figure out that efficiency, percent. Another way to do it, since work is really going to be the leftovers between QH and QL, H again is the high temperature reservoir, QL is the low temperature reservoir, and that's the heat in and heat out. You can think of it that way. Another way you can find it would be QH minus QL, that quantity over QH. Or you could also divide by QH and you get 1 minus QL over QH. Heat engine efficiency can be defined as the ratio of the work it does, W, to the heat input at the high temperature reservoir. It is clear that the efficiency of a heat engine will be a max if QL goes to 0. And I think you can see that. If QL would go to 0, that means you'd have a 100% efficient engine. But that's not practically possible. It can't happen in nature. It's not possible. The second law of thermodynamics says it's not possible. No device is possible whose sole effect is to transform a given amount of heat completely into work. So this engine right here, this theoretical engine, is not possible. We cannot take heat from the high temperature reservoir and turn it completely into work. There has to be some that goes out into the exhaust. That is what the second law of thermodynamics says. So another way we would find efficiency, E, is an ideal efficiency. Sometimes it's called the Carnot heat engine efficiency. And that's actually related to the absolute temperatures of the low temperature reservoir and the high temperature reservoir. So we can totally bypass the heat, Q, and actually go right into temperatures, absolute temperatures. So the ideal efficiency would be 1 minus QL minus QH. Again, you can see that the maximum efficiency would be when QL goes to 0. Well, TL goes to 0. Well, that would be a temperature of 0 Kelvin, absolute 0. It's not possible to ever reach absolute 0. We've gotten close, much closer than what nature has gotten, millions of a degree away from absolute 0, but it's not possible to reach absolute 0. Thus far, we have stated the second law of thermodynamics for specific situations. What we really need is a general statement. The total entropy of any system plus that of its environment increases as a result of any natural process. Biological evolution. Sometimes people point out biological evolution kind of violates this second law of thermodynamics. In actuality, it does not. An interesting example of an increase in entropy relates to biological evolution and to growth of organisms. Life forms are highly ordered systems, so at first glance it might look like the total entropy is decreased. Does evolution of such a system violate second law? Some people say it does. But it doesn't, because even though that life form is highly ordered, if you added up all the waste products that organism has produced, the total entropy of the system, including the waste products, will have increased. So the second law doesn't say you can't have a decrease in entropy in one isolated location, but for the entire system, the entropy will have to increase. So let's go back to your guess. Do you remember which one you guessed? What's the right answer? Right answer is C. Some waste heat must be produced. This is the fundamental property of nature when converting heat to useful work. You can't have a 100% efficient heat engine. In fact, you might like to know that your cars, if they're just completely gas, not electric, not hybrid or anything, the most efficient they could be would be, I think, around 20%. And that would really be a diesel, which has much higher engine temperatures than a typical car does.